Hey everyone, welcome to another video. Now, today I want to just take a little bit of a detour to look at something that confused me for a really long time when I was working with probabilities, and particularly when we were looking at these types of tree diagrams. Now, this video is purely a conceptual video, an investigative video. There are going to be no actual questions here. This video is purely designed for understanding why this formula itself actually works. Why do we just randomly multiply certain probabilities when we work with probability trees? Now, this is something that I never really understood when I was in school. I just thought it was like an arbitrary thing that we did. So when we looked at probabilities along a probability tree, we just times two of them together. You find out whatever the probability is along that branch, you multiply it together. Now, this video is going to give you, it's mainly centered on an analogy that I came across, which I find is quite useful for thinking about moving along these types of probability trees and why we actually end up multiplying these across. Now, what I want to talk about is to do with this probability tree. I want to use an analogy of a flow of people. So imagine I have, for example, 10 people starting off at this point. And they can take a series of different routes along this kind of map. They can go to A and then go up to A, go to A, then go down to B. They can go down to B, then up to A. Or finally, they can go down to B as well. We have 4 different avenues these 10 people can take. Now, we want to explore these. Now, this example is a little bit easier because all the probabilities are the same, but we're going to build up in difficulty, and this will hopefully show you why it is always going to work when we multiply these probabilities along the branches as we do these types of questions. Okay, now say my 10 people, when they came across this first fork in the road, going from A to B here, half of them are going to go to A. So let me write in here that half of 10, that's 5, half of them end up at A here, and the other half end up at B. So another 5 go here. Actually, let's pick a more nice round number for the purposes of this video. We're going to look at the number 12. So half of these 12 people go to A, so that's 6 of them, and then the other half go to B, that's 6 of them. Now, these 6 people on the top that chose this A, they're going to fork out again. So half of them are going to go to A, so in another color, that means 3 are going to end up at A, 3 are going to end up at B, because half of 6 is 3, and 3 of these ones that chose B first, half of those go to A. I get 3 of them, and I get 3 for my last one. So let's think about how we got from this starting number all the way to these end numbers. Now, I looked at this as sort of like a flow of traffic, a flow of people across, but let's say I wanted to show how I got to A. Now, what I did there is I took 12 and I multiplied that by a half and then by a half again. Oops. So now, doing this, I did it the long way, showing you at first, just forking out again, writing down all those last values. But we can show this in a quicker way by just doing this type of compounding multiplication as we go along those branches. So going through here, 12 to the 3 at the end, I can get by doing 12 times half times half. That's also the same as, well, half of, oh, actually, this is like 12 times, and half times a half is like 1 over 4. And then that gives me 3 here as well. So this breaks down into this. Now, what's actually happened here is that in working with probabilities, we are doing a very similar thing. We're going along these branches, but a shortcut for what we do to eventually calculate these types of multi-step probabilities is we do exactly that. What I did here, for example, let's say the probability that these 12 people go to A, then go to B. Like taking this route AB is the same as taking this first half of people, multiplying it again by another half. So going down to this next branch gives me the effect of multiplying these probabilities together. A probability that half are going to go here, half are going to go somewhere else. Now, I've got this illustrated with a few questions to show you that this works every single time, but let's look at another slightly different question here. So, now this is a pretty big tree diagram, so I'm going to have to zoom out. Now, let's say that, for example, let's pick a bigger number. So, for example, let's say 12,000 people started here. And we're going to trace the flow along some route here on our probability tree. So, I'm going to pick, for example, A to D. So I want to find essentially how many people are left when we traverse the path of AD. And we're going to see how that actually affects my number that I started off with. So I start off with 12,000 and, oh sorry, not 12,000, 1,200, and a third of these 12,000 people go down this path of A. So a third of 1,200 is going to be 400. Now at this point A, I've currently covered this part of my path. So I get to my A here, and 400 people arrive at A. And now, when they get to A, they can fork out in two separate directions. They can either go down to the path of D or the path of E. We're trying to find the path AD. So we're going to say that, okay, well, 5/8 of those 400 people went down path D. So if I take 5/8 of 400, I end up with 250. So I started with 1,200, I got to 250. Now, I did this by finding what a third of 1,200 was, and then 5/8 of 1,000 of that number was. But a simpler way I could have done that was I could have just taken over here 1,200 and then applied this root AD right off the bat. So I could have times this by 1/3 and then by 5/8 all together. And if you guys pop this in your calculator, you will see that this ends up equaling to 250. Okay, one more example. what if we get these really weird kind of fractions happening? So something that doesn't behave as nicely. We're going to do the exact same thing. You can pause this video and try a number of your own, but I'm just going to pick a random number here, 300. Now, I want to traverse the path of B, E. And to do that, I'm going to say, okay, well, these 300 people were split along these 2 points A, B, and 2/3 of those 300 go to B. So taking 2/3 of 300, I get 200. And then getting from B to E, now this thing is, I'm looking at the path BE. So now 3/7 of those 200 people end up going to E as well. So taking 3/7 of 200 gives me, okay, not a very nice number. That gives me about, well, it gives me 600/7, or if I round that up, about 85.7 people going down this particular thing. And what we're doing every single time, these 300 people going down BE, the root BE is going to be 300 times 2/3 times 3/7. So I'm doing the exact same thing as my initial formula that we all get introduced to in school. In all of these questions, I'm asking myself, for example here, the probability of taking the path A and A, so of going one A, then another A, is the same as this first path timesing the other path. Because as the people split off, they're getting split off. A fraction of them is going one way, a fraction of them is going another way. So that's where we get this multiplication happening here. Here, for example, we were looking at like the probability that these end up at A, D. Or that they cross A and they cross path A and path D. And we get that from taking this split, this fraction of when they go down path A, which is 1/3, and this fraction that they split off in when they go down this path of D. And we can do this really easily by just multiplying these numbers, these fractions I should say, through. And we get the exact same thing here. We're looking, for example, of the probability of going down path B and path E. And what ends up happening is a multiplication of these fractions, which we get down here. So this is just an analogy looking at, say, a flow of people with which we can show that probabilities work in the same way. They just end up being these compounding, multiplying fractions all the way through. So if I drew one last tree here, let's eliminate this flow of people now. And just look at this as a purely probability path, something that we're used to. So we have A, oops, I've already drawn something in there, A, B, C, and let's say this is 2/7, 3/7, and 2/7, and then A splits off into, let's say, 1/4, 3/4, B splits off into 1/2 and 1/2. Sorry, I should be writing these, whoops, I should be writing these in here. And let's go D, E. Let's move this across. and this across, and we get FG, and we have HI down here. And let's make this, I don't know, 2/5 and 3/5. No matter which way we decide to go, the fractions are going to multiply by each other because our probability is getting broken down. Because you remember when we looked at, for example, the easy idea of a coin flip, and we have 2 coin flips, our 2 outcomes changed into 4. In the same way, my outcomes are compounding here. They are multiplying. So say I wanted to go down the route of the probability route of, let's say, B and F. Well, that's going to give us a path. And all our tree diagrams and learning these notations for probability is about how we navigate through these. Which path do we take along our tree? So here we have B and F. So I'm going to first go down B, then I'm going to go up here to F. So whatever happens here, my probability of B, because I'm splitting my whole, so my certainty, for example, 1, because the sum of all probabilities ends up to a certainty of 1. We're splitting this probability of 100%, a certainty, into smaller bits. So I should actually write that here. So 1 certain. So we're no longer looking for a flow of people. We're looking at breaking up a certain 100% probability into smaller bits. And when we go down this path, first I get the probability of B. I'm finding a fraction of my whole, a fraction of my certain probability of 1, and I'm breaking that down. First, this first path going down B, multiplied by this next path going to F. And that gives me my 3/7. My probability here is 1. My certainty, my whole, is 1. So whatever multiplies by that is just going to give itself 3/7 times 1/2, which gives me 3/14. Now, this goes for no matter which direction I take. Where all we're looking at here is a navigation of my probability tree. So let's look at one more example to finish here. Let's look at the probability of going down the path C and then the path of H. So my certainty, my probability of 1, first gets broken down into 2/7, and then it goes down this path of H. So 2/5. So 2/7 of this go into C. 2/5 of this resulting thing go into H. It's the same as our flow of people idea we talked about. This is going to be, well, my certainty, my probability of 1, and sorry, I forgot to write 1 up here, but it doesn't affect our answer. 1 times 3/7 times 1/2 still gives me 3/14. But here, we're breaking down my certainty of 1, 100% chance, into 2/7 first. I get that by taking a fraction of a quantity. And then I'm taking a fraction of that quantity as well. I'm taking a fraction of that number. So as I go down my path, I keep multiplying through by the probabilities that lie on that path. So in this case, first 2/7. My whole certainty gets broken up into 2/7. And then that resulting thing gets broken up into 2/5. So we have this thing happening here. Or we can just think of it as all three of these numbers multiplying together, which is what you learnt when you first did this particular formula here of, and I've forgotten to write that here, but this is what we learnt when you first looked at this formula in school of my probability of C and H is going to be my probability of C times my probability of H. And that equals to this, which equals to 4/35. So hopefully this analogy helps some of you guys in your navigation of these probability trees, because it can get really hard and really confusing. And maybe for some of you, if you were like me, when you were first taught this, you wondered, well, what is the significance of this multiplication? Is that just an arbitrary operation we're doing and we're just doing it because the textbook told us so? Well, now hopefully we can see that it's not just a random thing that happens. This is a particular pattern that arises all the time when we look at splitting something in different directions, going down different paths of my probability tree. Now, if you guys want, you can try an example at home. You can say, for example, what's the probability of a E here? And apply this same principle that we've been doing the whole video, and that will hopefully give you some more confidence in navigating these probability trees and going through these types of questions in your own time. But thank you so much for joining me for this video. Like I said, it was a purely conceptual video, no real questions to look at, just an exploration of ideas. So if you made it to the end, I really appreciate that, and I will see you in the next one.